Okay, so this is going to be second order circuits. This is going to be pulled from the homework that I did for second order circuits. And when doing circuits for second order, we have a capacitor, inductor, and resistor all in either parallel or series. In this case, we are dealing with parallel. So, we're given some initial values. We're given the capacitor, the inductance, and the resistor value. So let's put that on another page really quick. Okay, so now that we're given our values for our inductor, capacitor, and our resistor, let us figure out how we're going to set this up. Right, right. Okay, so if you remember differential equations, ODE, we're going to set this up like it's an ODE. But when we're in parallel, what we're going to do is that this node above up top, right? This node here, we're going to do a KCL as everything goes down to this bottom here. We're going to call this ground. So this is what it's going to look like. And before we do that, we need to take note that um, capacitance dV dt is equal to current L di dt is equal to voltage, and V is equal to R times I. That's for resistors. Okay, now that we have that, what do we know about a KCL? KCL is for currents, right? So what we're going to do is we're going to denote I for all of these, for the capacitor, the inductor, and resistor as it goes down. So let's do a KCL. Let's add up all the currents as it goes down. The current for capacitor is equal to C dV dt. Okay. Well, for an inductor, it's going to be a little different. We're going to have to do it as so. So, to find I for an inductor, you may be like, well, that's the first derivative of I. Well, we're going to fix that. We're going to divide L over. We're going to have V over L. Actually, no, we're going to do 1 over L times V. And then we're going to integrate both sides. So it's going to be the integral from 0 to t, or 0 to infinity, of dt I. Let's pull L as a constant. So that is what I is going to be for an inductor. But we're not going to put that in there yet. We're going to fix that. And then we know I for a resistor is going to be uh, V over R is equal to I. Plus V over R is equal to I. Alright, so this is going to be, that's I. That's another I for the resistor. Now, we're gonna grab the first derivative of everything for this expression because this is a second order circuit. We need the highest derivative, or the highest derivative to be second order. So if we grab the derivative of everything, we can get rid of this integral, and we're left with 1 over L. Actually, before we grab the integral derivative of everything, we're gonna plug it in, just so for visual purposes. 0 to t v dt. That's equal to I for an inductor is equal to 0. Now we're going to grab the derivative of everything here. And that's going to give us C d2v divided by dt squared. I think that's where they're located. This is going to be 1 over r dv dt plus 1 over lv is equal to 0, because the derivative of this integral to get rid of all that, and you're just left with v. Okay, and we're going to get rid of this c here because we don't really like our highest order of the equation to be with anything. We like it by itself. So we're going to have 2d v dt squared plus 1 over RC, that's going to look familiar, dv dt plus 1 over LC times b is equal to 0. Okay. Now that we're this far, now that we have our ordinary differential equation, we're going to solve it. So it's much easier to solve this one with the old let v equal e to the mt. V prime will equal em e to the mt, and v double prime will equal minus 1 minus 1 m. No, you don't do minus 1. No, my bad. You grab the derivative again, you get m squared e to the mt, right? So what do we see? Well, what we see is that the second derivative is going to be m squared. We're going to factor that e to the mt because they're all going to have that. Plus 1 over RC. It's going to be m plus 1 over LC. And we have this quadratic here, basically. And we're going to have to solve that. To solve for m, what m is going to be, we're going to get rid of this e to the mt divided over. It's going to disappear. So we're going to do quadratic formula. So we know that b, negative 1 over RC, plus or minus the square root of 1 over RC squared, my bad, minus 4, a is 1, c, all over 2a. It's just 2, a is 1. Okay, well, let's bring that 4 out. We don't want that in there. So we're going to factor out a 4. We're going to fix that 1 over RC. We're going to make it 2 over 2, right? And then when you pull that 2 out of that square, it's going to make it 4, right? So it's going to be 1 over 2 RC squared. We're going to pull that out of the 2. It's going to make it 4. Okay. And since we're factoring out that 4, minus 1 over LC, it's going to be factored out. So we can bring that outside. It's going to be 2 root 1 over 2 RC squared minus, this is how they set it up, the square root of LC. We're just making that happen. And to fix it, we just square it again. 1 over 2RC. That 2 comes from this here. It's negative though. And then this 2 is going to cancel there, so it's going to go away. Plus or minus. And how you derive it is alpha is equal to 1 over 2RC. Wumbo is equal to 1 over root LC. Okay, and that's how it's derived. Right, that's how it's derived. So we know that what alpha and whatnot, what that's going to be. So we know alpha. We know Wumbo. I think it's omega is what it's called. So we know negative alpha plus or minus the square root of alpha squared minus omega squared. And we get 3 cases from this, as we know. And I'm not going to go over those cases at this moment, but we're going to go through this problem. So let's finish solving this, right? let's finish solving this problem. So let's figure out what alpha and omega are. What are they going to be equal to? So that number is going to be, use this calculator. It's going to be, okay, our values for alpha are going to be 1, and wumbo is going to be 3.16, 2, blah, 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 keeps going. So we got to do, let me do this really quick. And when we plug those numbers in, we get 1 minus whatever, and we get, under that radical, we're going to get negative 9. It's going to be 8.999999999, but it's going to round to 9, plus or minus negative 1, right? And we know this is going to be our second case. When we get a negative number under the radical, we get an imaginary number, 3i plus or minus negative 1. And the setup for this case, to convert it, it's going to be, well, to answer the question in this homework, since it's plus or minus, we have two solutions. We have negative 1 plus 3i, negative 1 minus 3i, and that's what it wants here in the beginning. Now it wants us to find the real roots. What is our s values going to be? Or we'll get to that in a second. Let's put in our values. So it's going to be e to the alpha times x. It's going to be e to the negative x e to the negative x. Doesn't have to solve all that. It just has us adjust the roots. Okay. Well, if you were to write this out, it would be e to the negative x cosine, my bad, c1 cosine of 3x plus c2 sine of 3x. And the 3 is from this, we call it, well, beta. It's 3. It's the one connected to the imaginary I. And yeah, let me go back up here, check my notes really quick. Okay, yeah, so we're good. That is the setup. Now for the problems for the homework, let's do a few scenarios. So if we were to adjust the resonant frequency, and the resonant frequency is known as the W slash wumbo. If we were to adjust to 100, what are the new roots in this equation? And we're just adjusting capacitance so that this new frequency is equal to 100. So it's going to be 100 is equal to 1 over root LC. We're adjusting C only, so we have to solve for C. We're going to square both sides. 100 squared. It'll get rid of that root. Multiply this by L. That's equal to 1 over C. I'm going to grab the inverse of this. And that'll give us C. And that'll give us that answer. Let's check that really quick. Okay. And then when we solve for C and plug it back in for alpha, we get alpha as 1,000, and we get the resonant as 100 still. So we have under the square root, we're going to get 994 plus or minus negative 1,000. So our real roots are going to be negative 1994, and the other one's going to be like 6. They round it somewhere. So in reality, this should be 1. This should be 90. And this should be 5. Oh, this rounds to 5. Okay. So those should be your real roots for S after you change this resonant frequency to 100. And for the last one, critically damped. Well, what value are they both going to be equal to each other? Right. So we're keeping our inductance and our resistance the same. So our formula is going to be 2 over RC. We have to set them equal because we want critically damped. And critically damped, let me move this back. Critically damped is when they are equal. So we need to solve for C. So we're going to cross multiply. We're going to get root LC is equal to 2RC. Square both sides. LC is equal to 4R squared, C squared. Divide both sides by C. L is equal to 4R squared C. And then we're going to divide that 4R squared over. And that will give us 0.01 or 10, 1, 2, 3. 10 millifarads. See. And that's question 1 done. Alright, so now we have another circuit, but instead we're given some initial values through this inductor and this capacitor. As it goes to ground, we're going to call this ground. Okay, so first, one of the questions that is asked by the homework is how do we figure out the initial values of the current through this inductor? Well, we know that as current goes down, it's negative 30 milliamps. And we know that the voltage is 90 volts originally going through everything. So it's 90 volts up here, which is also going through this resistor. So we know that 90 divided by 2000, which is the resistance, will give us current, which is going to give us 45 milliamps is equal to I sub R, we're going to call it. Now let's figure out the current through the capacitor. Well, by KCL rules, all the currents leaving must equal 0. So we know that 45 plus negative 30 will give us 15 milliamps left over. Sorry. But this must be equal to 0. This is positive and this is negative. So we need another negative to cancel out that 45. Negative 15 milliamps going down. This is going to be called I sub C through the capacitor. Okay. Okay. So now, let us find the values for alpha and omega to determine what our voltage as time passes on through that capacitor will be as it degrades from its initial value. because it's going to start at 90 volts, but over time it's going to keep going down and down and down, right? So voltage, as time goes on, will be through that capacitor. And this is going to be our initial value. It's 0 minus, right? It's going to be to the left of 0. And after 0 plus, it's not really 0 minus, 0 plus. It's starting at 0, it's starting at its initial values. So I'm not going to define them as 0 minus because there's nothing, it doesn't sit and it ends up there. It starts there. Initial value. Okay. So alpha is 1 over 2 RC. So we can simply find that by plugging in our answers, and we're going to get, let's see. And we get that alpha is going to be 25,000, and omega, or I call it wumbo, is 20,000, right? So we're going to get two real numbers for our cases here. 25,000 squared minus 20,000 squared. Square root that. We are going to get a really big number, but we square root it. So we're going to get 15,000 plus or minus negative alpha. So our real numbers are going to be e to the negative 10,000 t, c1 plus c2 e to the negative 40,000 t. Okay, this is going to be our general solution for voltage as a function of time. Okay, so now we need to solve for our constants, and we know that when t is 0, c1 plus c2 will be equal to 90. We need to find dv dt, and dv dt is going to be equal to I over c will be equal to dv dt. So the current going through that capacitor, which is negative 0.015 divided by capacitance, 10 times 10 raised to the negative ninth. Negative 15. It's going to be really big. It's going to be negative 15. 1, 2, 3, 4. And since it's dv dt, we need v as a function of time prime. So we're going to grab the derivative of this, and it's going to be negative 10,000 c1 minus 40,000 c2. I'm not like going super deep in detail with the explanation because I'm a little short on time today. So now to solve for the c1 and c2, we need to get a common factor for c1. So we're going to multiply the top one by 10,000 for all the numbers. And that's going to cancel it out. So 90 times 10,000 is going to be 900,000. And that plus that negative 15 million, I think, or it might be 1.5 million. It's going to be negative 600,000. And since C2 is 10,000, it's going to be negative 30,000 C2. And we're going to divide by 30,000, that negative 30,000. And that's going to give us C2, which is 20. And since C2 is 20, subtract that 20 by that 90, and we're going to get C1 is 70. So we know our C1 and C2 now. C1 is 70, C2 is 20. That gives us our answer. And now how do we get to the, now if we want to find current as a function of time through the inductor, well, what we're going to have to do is Let's see. Okay, so since we know voltage is a function of time through the capacitor, how that relates to the inductor as as follows here. If we divide everything by L and then grab the integral, we will get 2I. Right. So if we divide 70 by L, which is 0.25, and then since instead of derivatives multiplying by negative 10,000, we're going to divide by negative 10,000. So we're going to get negative 0.28 milliamps. And you just do the same thing for the other. And that's going to get us, so 20 divided by 0.25 divided by negative 40,000 gives us negative 2 milliamps. And there's no decimal here. So this is for the inductor. And that's how you relate the two. Or you could simply, instead of for your C1 and C2, you can plug in your voltages for the inductor. But yeah, this is how you find that. Okay. So I'm gonna do the rest of the questions some other time because I'm hungry. But this is one of the multiple choice. We can go over this quickly. Natural response over dampened, right? Defined over dampened, critically dampened, any of those, you need to compare alpha and omega under that radical, and that gives you 3 cases. And define critically dampened as we found by solving, um, if we're adjusting for resistance, you would set them equal to each other, and you solve for R. Because critically damped is when they're equal to each other. 1 over 2 RC, 1 over 2 RC is equal to 1 over root LC. Grab the reciprocal of both sides. 2RC is equal to root LC. Divide the 2C over, and you're left with R. And that gives us root LC 2C. Yep. Simple enough. And then for that circuit, we're going to have to actually solve that. That's another one of the cases. And I'll do that next time. Alright, now I am back with the video. Had to cut it. Had to finish the rest of it today. Whatever day we're on. So, stop doing that. Let's finish this question 5. We're on question 5 now. And we need to determine v sub t, not sub, v function of t. Right. And we are given all these values in a capacitor. Alright. Oh, we already did this one. No, this one's a little bit different. Hold on, let me see. Okay, the only thing that this problem changes is the value R of the resistor, so that's going to change probably a few things. So let's do our formula really quick. Square root of 1 over 2RC. Well, hold on, let's not do it that way. Let's do it. Root alpha squared minus 1 both squared. 1 over 2RC. 1 over root LC. It's 1 bow. This will be alpha. Plus or minus alpha. Okay, so let's figure out these values really quick. Let's plug them into a calculator. And we're dealing with 1 over 2, 2 times R, 2500 times capacitance. 20,000. 20,000. And the square root of L, 0.250 times 10 times 10 raised to the negative ninth. Oh, they're both the same. This is another case that we're getting here. So since the under the radical comes to 0, all we're left with negative alpha, right, which is negative 20,000. So how we do this case, when they are equal, this is called, I forgot the name, not critically damped. That's when we're dealing with no, this might be critically damped. You used to do it as follows. Negative e to the negative 20,000, right, C1 plus t plus C2 t e to the negative 20,000. I'm pretty sure they factor out that e to the negative 20,000, so it might look something like this too. C1 plus C2t. And we have to solve for our C1 and C2. Okay, so since we're actually for v as a function of time, we're going to plug in our starting v value, which is 90. So we're going to set 90 equal to C1. And that's it, because if you t at 0, C2 does not exist. It's going to be 0. So 90 is going to be C1. And that alone would give us the answer. We could figure that out. But we need to find C2. C2 is going to be... Alright, since we found C1, we now need to solve for C2. And to get C2, we need the second derivative of our function of v sub t. This is v sub t. Not sub, function of t, not sub, function. So we know, we need to figure out, right, because we know that I is equal to c dv dt, divide c over, and we got dv dt. And that'll be our v prime naught in ODE terms. So we need to find the current going through that capacitor. Well, we know the current going through the inductor. We just need to figure out the current going through that resistor, and we'll be there. So we can figure that out by 90 divided by 2500 gives me 0.036. Okay. Going down. Plus negative 30. So we're left. No, did not mean that. Plus, no, minus, minus 0.030. Got to the milliamps. So since that's a positive 36 going through that resistor, we need negative 6 milliamps through the capacitor. So negative 6, negative 0.006 divided by the capacitance. 10 times 10 raised to the negative ninth. Negative 600,000. Alright. So it's going to be negative 600,000 is equal to C1, which we already know is going to be 90, but C1, oh, we need to find the derivative of V sub t. So it's going to be negative 20,000 C1 plus the derivative of this function is going to be C2 e to the negative 20,000. And if we do it again, there's going to be a t in the other C2, so that's just going to become 0. So we know C1, so, and also, drop my pencil. Grab it. There we go. Okay. There's a t here. So we know this is just going to be evaluated as so. C1 plus C2. Okay, so now that we know C1, we can plug that in times negative 20,000. No, not plugging these numbers right. It's a big number. It's like 18 million. Okay. Since it's negative, we're going to add that over. So, missing a zero here. 600,000, not negative 60,000. So, negative 600,000 plus 3, 4, 5, 1, 8, 5 zeros. Get that number. One second. And C2 ends up being a very big number. 1, 2, 1.2 million? Whoa. Yep, that is the answer. Okay. And to the next question. Okay. So, there's this one. That's always fun. Find B out for t greater than 0. Okay. Let me write this problem up really quick. Okay, so we have this circuit here. We have an inductor and a capacitor on opposite sides, and when the time is equal to 0, the switch flips, and then the circuit looks like this. A resistor, a capacitor, and an inductor. And it looks like they're all in parallel. Alright? So, what we're going to have to do is figure out the initial conditions across that capacitor and the inductor. And once we do that, we can then solve for the values for t greater than 0 when the switch is flipped over. And then it's going to look like the second figure that I drew. This one. It's going to look like that. I need to solve for the equation that's going to give us the value for everything as time goes on, which is going to be an ODE. So, let me see the initial 50 ohms. I'm going to get rid of all this. It's a little in the way. Okay. So let's solve for these initial values. So, we know that, start with this capacitor. Since the circuit sat for a very long time, that capacitor is going to act like an open circuit. And since there's only one resistor in the way as this capacitor goes to ground, as this power source, there's only one resistor, so we know that all of that voltage is going to be onto that capacitor. So V naught is going to be 15 volts for the capacitor. Okay, now let's look at this inductor. Well, we know as this sits for a very long time, it's going to short circuit, like so. Oops. And then we have a current source here. Does this go down? It goes down, right? It goes down. Okay, so what's this current value this way? So we know that this current source is going to take the path of least resistance. And as this travels, it's going to take the short-circuited path, going that way. So as the current goes to down, we're going to call this ground still. As it goes down to ground, it's going to be a negative 60 milliamps since it's opposing the current source. Okay, so now that we figured out our initial values for this circuit, we can now solve for everything else. Okay, so let's go down to this one. Let's write negative 60 milliamps. For reference, it's going down. We got 15 volts. And what are we going for? Voltage as a function of time. Through where? Across the resistor. We want this. Across the resistor. Okay. So, voltage as it goes through that resistor. Well, let's just figure out the voltage for the whole thing, really. So, alpha is equal to 1 over 2 RC. Wumbo, 1 over root LC. And this is for parallel. It's different. You'll get a little different of an equation for a series circuit. Okay, now let's find our values. Let's use this calculator here. 2 times 125 times capacitance. 1 times 10 raised to the negative 6. 1 divided by that. Get 4,000. And Wumbo is going to be square root of L 0.0625 times capacitance 1 times 10 raised to the negative 6. This is also 4,000. Oh, goody. So it's going to be 0 under this root. And we're going to be left with negative 4,000 plus or minus. So we have the same case again. C1e to the negative 4,000 t plus C2 t e to the negative 4,000 t, or written as in the problem probably e to the 4,000 t C1 plus C2t. Factor that out. Okay, now let's solve for C1. C1, if we do this as a voltage as a function of time, C1, our V naught is 15. So we know since t, when you set it equal to 0, C2 is going to disappear. So C1 is going to be 15. Alright, now we must solve for C1 and C2. So that since we know when we set t equal to 0 for the first, we know C1 is going to be equal to 15. Right. So let's get C2. We need to find the first derivative. We're going to use I is equal to C dV dt. Right, divide C over, and we need to figure out the initial current through that capacitor. And we know the initial current through that inductor is going to be negative 60 milliamps, and we know that voltage is 15. 15 divided by 125 is going to be the initial current through that resistor. Okay. 15 divided by, we get 0.12. Okay, we're going to need a negative 60 milliamps for the capacitor as well. So it's going to be negative 0.06 divided by capacitance. 1 times 10 raised to negative 6. Look at negative 60,000 is going to be our V prime naught. Okay, and then if we grab the first derivative, we're going to get negative 4,000 C1 plus C2. And you have to grab the derivative of this. And if you set t equal to 0, you're just left with C2 for that. So it's nice to remember that. Quick math. 15 times negative 4,000. Okay. Negative 60,000. Okay, C2 is 0. C2 is 0. So we just have 15 e to the negative 4,000 t. That's our final answer. Yep, that's what we get. Beautiful. Alright, oh, let's fix that. Let's go, I'm going to go to the next problem now. Okay, so for number 7, we're dealing with some different responses here. Okay, we're dealing with that circuit up top. Alright, so really all we're doing is solving for a bunch of these different ones. We're going to have the same setup for all of them. Same circuit, right? So let me clear this up really quick. Okay, so for this circuit, we're using this same model here that's shown right here for all of them, right? So now we just need to plug it in to all of them. We know alpha is equal to 1 over 2 RC. We know omega is going to be equal to 1 over square root LC. And we know the formula. We just need to solve for alpha and omega, and we'll get to the where we need to go. Okay, so let's solve for this. 2R, 2 times R times C. So we got resistor 2 times 100 times capacitance. 16 times 10 raised to the negative 6. 1 divided by that number is 312.5. Omega comes out to be inductance times capacitance. 1250. It's a big difference. We're going to get an imaginary case with cosine and sine. So 312.5 squared minus 1250 squared. So we're going to get 1210.30 I, since it's imaginary, plus or minus negative 312.5. Okay. Let's see what we got here. Alright. Yeah, so this is our alpha, this is our beta, which is going to be cosine of 1210.3 t plus C2 into C1. Don't forget that. Sine 1210.3 t times e to the negative 312.5 t. Okay. So now we solve for our C1 and C2. So when t is equal to 0, cosine is 1 and C2 is sine is 0. So our initial value is starting at 10 volts, so 10 volts is going to be equal to C1. Right? And to solve for the C2, you grab the derivative of this function, which that cosine is going to become a sine. So you need to focus on the sine becoming a cosine, which is going to be the product of negative e to the t power and the sign. So it's going to be a negative, it's going to be C2, 12,010.3 cosine, and that's going to be it. Well, you're also going to have e to the 312.5t. Let me think of the derivative over here. Yeah, we're going to have plus, no, it's going to be minus 312.5 C1 cosine 1210 t e to the negative 312.5. So this is all going to disappear. And you're just left with, we need to find this value, I over c is equal to dv dt. To find that value, we need to find the current going through the capacitor, which is going to come out to be, we know the initial current through the inductor. We need to find the current through the resistor, which is going to be voltage, 10 volts divided by 100.1. And okay, so it's going to be negative 0.15 divided by capacitance. It's going to be 16 times 10 raised to negative 6. It's negative 9,375. So we know C1's going to be 10. So we know it's going 312.5 times 10. Add that over. Divide by 12, 10. And we get negative 5.16 is equal to C2. Is that right? It is right. Woo! We did it. Now we have to do another one. I don't really feel like doing all of them. That's a lot. But I'm going to do them anyways. Okay, I'm going to erase this really quick and do it over again. Actually, since these are all the same in their own way, I need to move this over. I need to fix that. There we go. Since these are all the same, I'm going to skip these. They're all the same format, so it's a lot repeated. I don't want to keep doing the same problem. I'll do multiple problems of the same type for when I make the study guide though. I will make a study guide. Not like a study guide, but I'm going to do like a final couple videos of examples from each of the chapters. Let's do 8. So this is a step response. Okay, the last part is pretty hard to find, so I will show how to do that. It's not that hard really. You really just square your function and divide it by the resistance. Like, or no, you do voltage squared divided by resistance, which is equal to power. It's pretty simple. Nah, not really simple, but let's start this problem. I'm gonna draw it out really quickly. Okay, so we have our circuit. My bad. Did that so wrong. Okay, so now to figure out the solution, we need to find the voltage across that inductor. To do that, we are going to need to do some KVL stuff. point. So if we have 3 divided by 8. Okay. So the voltage initially is going to be 3 divided by the inductance. 8 will give us dV, no, di dt, which is 0.375 amps per second. Right. And so, with knowing this, which is I prime naught, we can figure everything out that we need to know. So we know 1 over 2 RC alpha. Wombo is going to be root LC over 1. We need to just figure, plug and chug our values in. 2 times R, 250, times capacitance. 50 times 10 raised to the negative 6 divided by 1. This is going to be 40, and 8 times, the square root of 8 times capacitance. 1 divided by that. 1 vote is 50, so we're going to get a negative number underneath since alpha is less than 1 bow. And we're going to get 30i. Okay, so our setup's going to be C1 cosine of 30t plus C2 sine of 30t e to the negative 40t. Need to find our C1 and C2. So at t is equal to 0, cosine will be 1. So C1 is going to be 40. No. C1 is going to be equal to I naught, which is 0.050 amps. And C2 will be equal to, well, it's going to be 0.375 is equal to the derivatives of the ones up top, because it's dv dt, so we need the derivative of this function. Okay, so we're going to have 30C2, okay, and we're going to have minus 40 C1. That's going to be our cosines that are going to be equal to 1 at 0. Those are going to be the only ones. Yeah. Okay, so C1 is 0.05 times 40, 0.375 minus plus 2 divided by 30. Okay. And does that match our answer? Let me check really quick. I don't want to say anything. No. No, it does not. Got 0.08. Okay, let me double check my work. 30 cosine 30 C2, right? Oh, let me see. Is it milliamps? Make sure my values are right. Let me take this down. Okay. So yeah, it's gonna be 0.05. Is I naught. So 0.375. Let me see. Hold on. Alright, my mistake. When it comes to finding um, there's this first constant, I naught. You set it up as the following. I naught is equal to I final uh, minus, or is it minus C1 or plus C1? Plus C1. So C1 would end up being 0 because I naught is 0.05 minus I final, which is also the same value. So C1 is 0, so it's going to be 0.375 divided by 30, which gives you 0.0125 C2. Right, and that's going to give you your final answer. Now, for this one, since, I final approaches its final value, you do it as the form uh, 0.05 plus, or no, it's minus, no, it's plus, 0.0125 e to the negative 40t times sine of 30t. That's how that one is set up. It's a little bit different because its final value is approaching a number. It's not approaching 0. So this is why this one is different. When you have a value that it approaches to, when it goes to infinity, you add that to your final answer, like we just did. But when you're solving for C1, you need to make your I naught equal to I final plus your C1 and your C2 when you're doing that. So, right. And then when you find VL of t, all you're doing is, you have your answer here, which is equal to I sub t through the inductor. We know that V is equal to inductance di dt. Find a derivative of this and multiply it by L. And you get voltage. Trust. You will. You will get this answer. And then for this, you just do that top one, or this is voltage, right? You do voltage squared divided by 250, which is your resistance. So, and this is power this is the for the resistor, right? So, you need to find the voltage first, and then you need to find the voltage through the resistor. So, if you were to look at this circuit, right? How would you find the voltage through the resistor? Well, if you do a little KVL here, we know that the resistor is going to have mm, we're dealing with R plus minus, and we're going to start right here. So that's going to be the negative. R is going to be the negative. You're going to plus that over. My bad. Let me see. Yeah. So when you're doing that, when you find the voltage through the resistor, you need to do a KVL here for sure, right? You're going to end up with negative 12.5, and then that function for V sub t plus V voltage through the inductor uh, plus 250, or no, plus R, right? We're solving it for R. It's equal to 0 minus the R over, distribute that negative, you get 12.5 positive minus voltage L of t. Make sure to distribute that negative and that will give you your answer, right? And then divide by that squared. So I am slacking when it comes to this explanation, I'm not gonna lie. I'm low-key giving up a little. Probably because I'm a little tired. This one, I'm just gonna give it to you. Underdampened. And yeah. If you want to see the work for this, you can get it from, um, I'll show you the work on my, hold on, let me pull up the work real quick. Alright, this is the work I had for this before. Here's the work for the previous problems. And here's the work for this one. So at t is less than 0, the switches are flipped like shown. So that capacitor gets charged and that inductor gets charged to 5 volts for the capacitor and 0.05 amps for the inductor. And then it flips. And then you're left with this state of the circuit. Um, the capacitor is going to approach a final value, but the inductor will approach 0 because once that capacitor is fully charged, it's going to be an open circuit. It's going to get 50 volts and nothing else is going to get powered because it's going to act like an open circuit. Okay? Okay, so you set up your formula like shown, and then this one's a little different. Since this one's in series, your formula is going to be R over 2L is your theta, and your wumbo is going to be still 1 over root LC, and for your alpha you should get 111 for wumbo, and 0.11 for wumbo, 111.11 for wumbo, and then once you grab those numbers, you should get this for your values, e to the negative 33.7t plus c2 e to the negative 366.3t, two real roots, and then you solve for your c1, and you set it equal to negative 45, and you get that from, let me think, not that one. So negative 45 is going to be, negative 45 comes from the initial condition, ooh, whoa, the initial condition for the capacitor is 5 volts, but its final value is 50, right? Because all of that voltage from the voltage source will charge that capacitor. So you subtract the 50 over, you get negative 45, and this will be your first equation. And then you need to grab the first derivative here for this circuit from the general solution up top. And then you need to find dV/dt. So you find the current through the capacitor and divide it by C. And we're going to find that the current through the capacitor is going to be initially, right, it's going to change instantaneously And since the current through the inductor is 0.05, so 0.05 divided by the inductance, 1. Oh, that is not right. No, capacitance. What is the capacitance value? 81 microfarads times 10 raised to the negative 6. And we get 0.05 divided by this. We get, yep. So your current's going to be the initial value through the inductor, which is 0.05, divided by capacitance. And you'll get this value over here. Okay, and then you just solve simultaneously. And there you go.